Okay, we are going to begin looking at applications of the derivative. We've been spending quite a bit of time learning how to find the derivative of a given function. We looked at many rules involving the product rule, quotient rule, chain rule, the rules for the derivative functions, for the inverse trig functions. The derivatives of the trig functions is what I meant to say, and the derivative of the inverse trig functions, exponential and logarithmic. So one of the main uses of the derivative is as what we call a rate of change. If you're following the textbook actually does this sort of in the middle of the process of finding all the rules for differentiation. So in a sense, I'm going back if you're following pace in the textbook, which is section 3.4. So just recall for any function, y is a function of t, the average rate of change of the function with respect to t over the interval from t equal a to t equal b is given by this expression here. So what are we saying here, right? If you look at this, this is really nothing more than the difference quotient over the interval from a to b. All right, because what we're doing is we're finding the change in the independent variable over that interval, right? If I go from t equal a to t equal b, then b minus a, if you will, is the distance, right? Or the change in the value of the independent variable. And then f of b minus f of a is the change in the output to the function over that same interval, right? And so really, if you're looking at the graph of the function, this is the change in the height, if you will, the y value, right? The vertical directed distance change over the horizontal change. It's a rise over run. It's a slope, right? So if I'm looking at a function from a to b, let's say this function looks something like that, I don't know, right? Then from what we're looking at is essentially the slope of the line that's connecting these two points, right? Because this point is what? This point right here is the point a comma f of a. And this is the point b comma f of b. So the f of b minus f of a is the change in the height as I go from this point to this point, and the b minus a is just the distance between b and a here, right? And so it's the slope of this line, and so it's the average rate of change. So as we move from a to b, right? If I want to say what's the average rate of change, it's really just the slope of this, what we sometimes call secant line. Okay, so that's something you should have learned in pre-calculus, and we'll look at applications here in a little bit. But you know, if a common situation is the function f represents the position of an object undergoing linear motion, and it's the distance from a fixed point, is what this function gives over time, right? And in that case, the horizontal axis could be time, right? Say in hours or something, and then the output to the function could be the distance traveled, say in miles. And so what do you get for your average rate of change? The change in the output is the difference in miles, the total miles you traveled, right, over what? The given time interval. And so you get a rate of change of what? Miles per hour. So that's something that's real important, and we're going to talk about that. Now, that's pre-calculus. Calculus, then, we can talk about the instantaneous rate of change, right, or just rate of change. That's what? The derivative, right? So if I'm trying to find the instantaneous rate of change at t equal a, at that exact instant, right, what are we talking about there? Well, if I'm just talking about right at that point, I can't calculate, I don't have another point to form a line. So what are we talking about? We're talking about the slope of what? The tangent line, the line that's just tangent to that point, right? The slope of that tangent line, that's f prime of a, and that's the instantaneous rate of change. Okay. All right, so let's see if we can put these to practice. So first of all, I just want us to understand in words what's happening. So here's an example of a function. V is g of t. Let that function be the volume in gallons of water in a huge tank t seconds after it begins to be drained. So it's important to understand what this function gives us, right? If I plug in the number of seconds, t is in seconds, after we begin to drain this huge tank, right? If I want to say what's happening, 30 seconds after we begin to drain it, and I let t be 30, what's the output to the function? The output is what? V is what? The volume of the tank in gallons. Okay? So input input the time in seconds, output the volume in gallons. Okay, so explain in words what this statement means. G of 30 equals 950. And we're going to write a complete sentence. Now what I'm not looking for is when I input 30 into the function g, the output is 950. Or g of 30 is 950. Yes, that's true, but that's not what I'm asking for. When I say explain in words what this statement means, I mean in context of the actual function and what it represents. Okay, so let's see if we can do that. So first of all, 30, what's that represent? That's the input, that's the time, in seconds after it begins to be drained. So let's start there. How many seconds after it begins to be drained? 30 seconds. All right, so 30 seconds after the tank begins to be drained. Okay, so that's what that represents. So what exactly is happening? Then what? What's this 950? That's the volume of water in the tank in gallons. So 30 seconds after the tank begins to be drained, there are 950 gallons of water in the tank. And that's what I mean by explaining in words what the statement means. Okay, so I do that one. That's really a pre-calculus question, right? Just understanding what function notation means. So g of 30 equal 950 in this context means what I've written here. So in a complete sense. Now, what does g prime of t represent? And again, we're going to write a complete sentence. Well, g prime of t, let's look up here, right? The derivative represents what? The instantaneous rate of change, or just rate of change. Okay, I'm just going to use rate of change. So it's real important. This question, if I ask you, should be written basically the same way. Of course, this depends on the actual information given for the function. But g prime of t is what? The rate of change, right? Instantaneous rate of change, or rate of change. And what is it the rate of change of? Okay, it's the rate of change of what? Y. Right here, y. Y is what? The output to the function. What's the output to this function? What's the dependent variable here? V. Right, that's the volume in gallons, right? So it's the rate of change of the volume of water in the tank. Right, so it's the instantaneous rate of change, or rate of change of y, which in this case is, we're talking about v, right? V is g of t, which is the volume of the water in gallons in the tank, with respect to what? T. So what are we with respect to here? With respect to t here as well, and so that represents what? The time. So with respect to, and I'll say elapsed time, since it's the number of seconds since. Okay, with respect to the elapsed time. So that's what it means. And so the key is, anytime I ask, explain with words in a complete sentence what the derivative represents, I don't want you to say g prime of t is the derivative of t, of g rather, with respect to t. That's not what I'm asking for. All right. I'm asking for this interpretation, right? What it indicates in the context of the problem. And key to that is you've got to have the rate of change here. That's going to be critical. It's not the change, it's the rate of change. There's a difference. It's not the change in the volume of water in the tank, it's the rate that it is changing. And also, right, with respect to, you always have that here. And so it's the rate of change, and it's always going to be the dependent variable or output to your function with respect to what? The independent variable or input to the function. Now, what are the units of g prime of t? Well, the units of the derivative or the rate of change of the volume of water with respect to time are easy. It's always the output units to the function, which are going to be what? V is what? The volume in what? The units are gallons. So this is gallons. And then it's per what? Per units of the independent variable, right? Which is what? Time. And what's our time unit? Time is measured in what? Seconds. So it's gallons per seconds. That's what we mean by the units of the derivative of the rate of change, g prime of t. If you want to use some, short abbreviations for gallons and seconds, you can write this way. The slash usually means per, right? Per divided by, in a sense, second. So gallons per second can be written that way as well. Okay. Now, in this situation, given, should g prime of t be I always positive? I guess that's 1 technically, Roman numeral 1. 2 always negative, or 3 alternating between positive and negative. What should it be? What should it be? Well, notice this is what? The number of seconds after what? It begins to be drained. What's that mean, to be drained? What's that tell you about the volume level of water in the tank over time? Right? If I was looking at the graph of the volume with respect to time, what would we expect to see? We would expect to see this going down, right? Going down as time progresses, right? So draining the tank, right? So at any point in time, what are we talking about? G prime of t. That's the slope of the tangent line. If I pick any point and look at that corresponding tangent line, what do we know about that tangent line? What would we know about it right at that point? Well, we would know the slope is what? Negative, right? Which means the sign of g prime of t is always going to be negative, and that's because of the problem that we are draining water out of the tank. Okay. If it was positive, that means what the rate of change is positive means we're increasing, right? The gallons in the tank are increasing. And that's not the case if it's being drained. Okay. Let's take a look at another example. Okay, a little aeronautics or aerospace engineering problem. Let D equal h of v be the drag in pounds on an airplane flying at v miles per hour. So we input into this function the speed, if you will, right? The airplane is flying at v miles per hour. This could be the speed, right? So input the speed in miles per hour, and what's the output? D, the drag, which is a measure in pounds. So drag is the force exerted on the aircraft. If you've ever, driven down the road in your car and stuck your hand out the window, right? You feel that force against your hand, right? That drag on your hand from the air, and that happens in aircraft as well. Okay, so again, what does h prime of v represent? So we answered that question very similar up here. What does g prime of t represent? So again, I'm not looking for h prime of v is the derivative of h. What I'm looking for is what? H prime of v, it is the what? The rate of change of what? The dependent variable, which is what? The drag, the rate of change of drag on the airplane, right? With respect to what? What we said was flying at this what? v miles per hour, we call that what? The speed, right? With respect to the speed of the airplane. That's the input. What are the units of h prime of v? Again, dependent variable units. The outputs are drag in pounds, so it's the rate of change of the drag, which is in pounds, so it's pounds per what? Input units. And the input units are the speed is the input. What are the units for the speed? Miles per hour. That's a little crazy. We've got two pers in this sentence, right? Pounds per miles per hour. So it's pounds per mile per hour. You can also write it in shorthand notation. If you know pounds typically are designated lb. I think that has something to do with Latin for scales or weight. But lb is typical designation for pounds per what? Units. Miles per hour. One way is miles per hour. You can abbreviate that way. Or some of you have seen, no doubt, mph for miles per hour. That's another common abbreviation. So something like that, it would be fine. Okay. So there it is, pounds per miles per hour. So finally, explain in words what the statement h prime of 600 equals 350. Okay, so be very careful here. We basically have all the things we need from the previous two. So the minute I see h prime of 600, what is that? That's the what? H prime of v represents what? The rate of change of the drag, right? And we're inputting 600, right? The input is the what? V is what? Miles per hour. So that's at the speed of the aircraft, 600 miles per hour. So at the instant the airplane is flying at 600 what are the units here? We're going to put that in miles per hour. The what? H prime of 600. What does H prime represent again? We just said it, the rate of change. The rate of change of what? Of the drag on the airplane. Right? So what this represents, right, is what? 350. But what are the units? 350 what? Is this pounds? No. H prime, right? What are the output units? We just said, what are the units of H prime? What are the units? Pounds per miles per hour. Pounds per mile per hour. Okay. So what we're saying is that instant, roughly, the airplane is flying 600 miles per hour. If we have a change, what's this mean? 350 pounds per miles per hour. So a 1 mile per hour change, right, is going to result in what? 350 pound change in the drag, approximately. That's what the slope of that tangent line is telling us. That's what the derivative is telling us. So 350 pounds for every mile per hour increase. Okay, so that's maybe seems pretty extreme to you, but that's what it is at this instant. Right now things may be changing. Right, the graph is not probably linear necessarily, but right at that instant, right, that's what the rate of change of the drag on the airplane is. Okay, so real important to get the units correct here, and make sure you have the rate of change right when we talk about the derivative. And that's the meaning of these things. Okay. Let's look at one little example. We'll move away from using words, but let's look at one little example here. The speed of sound, which is represented by V, measured in meters per second. So it's how fast the sound is traveling. With respect to air temperature, which is measured in kelvins, kelvins is a measure of temperature, is given by this equation here. Okay. So let's find the rate of change of the speed of the sound with respect to the air temperature. So what is the rate of change of the speed of sound with respect to the air temperature? What is that thing? Right. That is dV dt. The derivative of v with respect to t is the rate of change of the speed of sound with respect to the air temperature. Okay, so first of all, we would probably rewrite this now. V is what? 20 square root of t, I'd write as t to the 1/2 power. And so now I can find dV dt. Since I know what v is equal to, what is dV dt? Well, constant multiple rule. Now we're going to use our rules for finding derivatives. Pull the 20 out. T to the 1/2 power rule. Bring the 1/2 down. Subtract 1 from a half. Right. And then multiply 20 times a half, I get 10. And then t to the negative 1/2 is what? 1 over t to the positive 1/2, or square root of t. I'll go ahead and write that. T to the 1/2 in the bottom, square root of t. So there's my derivative. Okay. And now we can answer this last question. What is the rate of change the instant the temperature is 400 kelvins? And then give correct units. So we're looking at evaluating dV dt, and when we're evaluating this type of notation for the derivative, the Leibniz notation, we'll evaluate by doing a vertical bar. And then what are we evaluating at? When the temperature is what? 400 degrees Kelvin. T is the temperature, right, in Kelvin. And that's going to be equal to 400 then. So now what is this derivative evaluated at this thing equal to? Well, I just plug in T is 400 and I evaluate. Square root of 400 is 20, and that simplifies to what? 1/2. What are the units? What is the rate of change of the speed of sound with respect to air temperature? Well, there's the units here. Well, it's dependent variable units per independent variable units. The dependent variable, the output to the function, is what? The speed of sound, right? And what are the units there? Meters per second. Per what? The independent variable is T, which is what? The temperature in what? Kelvins. So we'll abbreviate kelvins with a K. And there is your derivative. So what this is saying is basically for every 1 degree in Kelvin increase in temperature, then the speed of sound is going to increase by 1/2 a meter per second. 1/2 a meter per second. Okay. I think the speed of sound in standard atmosphere, and I'm not sure what temperature, but it's about 300 or so meters per second. I think that's correct. I could be wrong, but something like that. But at any rate, so this is saying that temperature has an effect on that, interestingly enough. Not a whole bunch compared to actually how fast the speed of sound is. Okay. So we're going to stop here, and in the next video we're going to continue with this idea of rates of change, but we're going to look at a particular type of function. I mentioned it already, one in which the function gives the distance or linear distance traveled by an object undergoing linear motion. And we'll talk about what the derivatives then represent there.